In this module, we'll be considering the first half of Chapter 16. Chapter 16 is one of the bigger chapters in the book, so we're breaking it up into two different modules. We're going to focus in this module on the first half of the chapter addressing fossil fuels. When we look at the issue of energy supply and energy demand, we recognize that when these two are well balanced, we have relatively few problems. But when we have a lot more demand than we have available supply, then we have what are known as energy shocks, and they have significant impact on both our national and global economic development. It can lead to recession and inflation and a number of other economic difficulties, job loss. It's also true that we'll eventually reach peak oil production, a point where our global production of oil will be at its maximum, and then in the subsequent years we'll begin to experience decline in the available oil that's being produced across the globe. And that's definitely going to be a shocking experience that's going to have the potential to significantly impact global economies. This is not a matter of if this will happen. It certainly will happen. We have a limited supply of oil available to us on Earth's surface, but it's just a matter of when will peak oil experience and the amount of oil available to us begin to decline. Planning to conserve oil and transition to alternative energy sources will be critical in the coming decades. It's already proving true now as we're trying to avoid some of the oil price shocks that our economy has had to absorb, but it's going to increasingly become important in the coming decades during your lifetimes. Oil is being consumed fairly rapidly relative to the amount of additional resources of oil that are being found. If we look at discovery, that peaked around the late 50s or 1960, but our consumption of oil has continued to increase over the decades subsequent to that discovery boom, and so we're using up the known resources in oil and gas supplies. When will peak oil happen? Peak oil will be the time at which production hits its maximum. Sometime it's estimated between 2020 and 2050. And if our demand for oil continues to increase beyond that peak, we're going to be developing an increasing energy gap in the difference between the demand and the available oil and gas resources. So the size of that gap may continue to grow if we haven't come up with ways to take advantage of alternate energy sources. When we look at energy supply and demand issues, from a few more facts we want to consider. About 90% of U.S. energy consumption comes from fossil fuels. That is, and here I'm grouping fossil fuels as coal, oil, and gas. Fossil fuels are non-renewable. We only have what's available in Earth's near crust, and once those are used up, there's nothing more that's going to be available to us. You can't make coal or oil or gas in any meaningful supply quantity. So once we use up what is available to us near Earth's surface, that's it. Only about 10% of U.S. energy consumption comes from power generated from either hydroelectric power or from nuclear power. Projections of energy and supply and demand are difficult. We've made estimates before, and the number of assumptions that you need to make are many, and the amount of new technologies that get developed can help us become more energy efficient, making our estimates wrong in one direction, or new technologies become available that increase the total demands on energy, which cause us to make mistakes in the other direction. We need to continue to develop research and evaluate potential energy sources and conservation practices to ensure sufficient energy is available to us to maintain our industrial society and our quality of life and our quality of the environment. When we look at the amount of oil that's being uh, used in the United States, we can see that the largest fuel source is oil, shown in orange, followed by natural gas, shown in green, and then we get to coal, shown in the blue line. And this traces the U.S. Reliance on these various fossil fuels over the last few decades. Fossil fuels owe their origin to the geologic cycle. Energy is stored in the form of organic material and it's transformed after burial. Environmental disruption caused by exploration and development of fossil fuels must be weighed against the potential benefits of finding and then getting access to additional forms of fossil fuels. Exploration and development, the drilling, the mining of fossil fuels has a significant environmental impact, and there's no denying that. We'll focus on some of that in this module, but we've seen it in other modules as well. Coal makes up about 20% of U.S. energy consumption, so it's a significant chunk of what we depend on. But when we're going to talk about coal distributions, one of the things you'll see is that relative to other parts of the globe, the U.S. is also relatively rich in the available coal resources that we have access to or that are in U.S. territories. How is coal formed? Oxygen-deprived plants decompose and accumulate upon burial to form peat. When the peat layer is inundated by overlying sediments, then you begin to have the sediments squeezing the peat, and the increasing sediments cause it to become increasingly compact and allows for more and more of the volatiles component, the gas components, to get squeezed out of the peat. As it gets compressed, the percentage of carbon increases in the compressed peat. That process is depicted here. We have some sort of plant life that's in the oxygen-deprived decaying state. If it gets trapped by sediments, it can become peat. With further burial, it begins to compact. With additional burial beneath additional layers of sediments, then it gets compressed more and can eventually progress toward coal when its carbon content gets high enough. This leads to the topic of classification of coal. There's a number of different ways that we can classify coal. We might base it on the percentage of carbon and heat value, and in that case, the best class of coal would be that which is high in carbon and has a relatively low moisture content. We might also classify coal based on the sulfur content, because sulfur ends up being one of the most environmentally harmful components that coal has, and there are low sulfur coals that release less sulfur dioxide when we burn it, and there are also high sulfur coals that become problematic when we use them. Here's a graphical depiction of different types of coal. When we move in grade, that is in increasing quantities or percentage of carbon or heat content, lignite is typically the lowest grade of coal, followed by subbituminous coal, followed by bituminous coal, followed by anthracite for the most developed or most highly developed form of coal. Anthracites in general, on average that is, have the highest heat content per kilogram. And another way of looking at these different uh, classes of coal is to look at the components. And if we look at the moisture content, the volatiles content, and the carbon content, we see that lignite tends to have relatively high moisture content, intermediate volatile content, and relatively low carbon content. As we move up in grade, we see that the moisture content tends to decrease, the volatiles content will ultimately decrease, but the carbon content is the one that increases when we move up in grade of coal. How are these different grades of coal distributed across the United States? We have very few pockets of anthracite coal left available to us. We have larger quantities of low volatile content bituminous coal and subbituminous coal. We also have fairly abundant supplies. We also have extensive quantities of lignite, which is one of the lowest grades of coal, remember, but in those locations where that's the only type of coal available, then that's a resource that people in the region often wish to take advantage of. How does the U.S. do in terms of the amount of coal we have relative to the rest of the globe? It turns out that we have significant amount of coal reserves available to us. If you look at Europe and Russia, you'll see extensive amount of coal present there. Australia and Southeast Asia have significant coal supplies, but Africa has relatively modest supplies. South America has extremely low quantities of coal available because of their geology, and the Middle East, you'll see, has a very low fraction of the world's coal available to them. Coal, if we look at what are the potential environmental impacts, the mining of coal is the first place where we have to look at the types of impact that the environment takes from us taking advantage of this resource. Most of the coal that we use in the United States comes to us from surface mining or strip mining, which I also called open pit mining. And one of the major consequences of mining are the disturbed lands and the coal sludge or the portions of the tailings, what's left behind after coal production has been completed in an area. So there's significant amounts of coal sludge in the Appalachian mountains that's becoming an increasing concern for the people living in that region. Coal mining has a number of inherent impacts on the area and region in which the coal is being mined. The actual impacts depend on the region, depend on the geology and soils in that region and the climate in that region. Acid mine drainage is probably one of the biggest problems with coal mining. After the land has been disturbed, the potential for that disturbed soil to lead to acidic or low pH groundwater seeping through the disturbed soils is significant. In some areas, it's a major problem. In fact, some of the worst problems in acid mine drainage come from coal mining, not from metal mining. In addition to the acid mine, the fact that the water filtering through disturbed land might become acidic, we also have the fact that changes in the topography can cause water diversion. Water that had been running off or infiltrating and supplying one watershed can instead supply another watershed. So we're making some rivers bigger and some rivers smaller. And that change in the watershed might cause erosion in and on of its own self, and disturbance to other ecosystems. Reclamation of land after mining has been completed is an ongoing problem. Our reclamation of disturbed lands in the past has been atrociously poor in some parts of the United States and globally. But increasingly in the United States, we have federal guidelines that govern how strip mining must be completed, that the land is supposed to be returned to something closer to its original form in terms of the vegetation and the stability, that is the soil's ability to to keep from eroding and to have gullies form and sediments move downstream. So that's now a required step in the mining process. However, it's very difficult to fund this. If the mine continues to want to develop and produce coal in the area, then they're going to also have incentive to progress, to continue to allow the land to be reclaimed or restored, to have the vegetation restored to something closer to its original condition so that their mining production can continue. However, once a coal resource has been used up, or if a company goes bankrupt and stops doing business, stops mining in an area, then ensuring that there's enough funds available to reclaim the disturbed lands is something that governments are often working with to find ways to make sure that this final step in the mining process takes place, whether or not the company continues to be in existence or has gone out of business at the end of the mining life. That's led to the development of the concept of performance bonds, that before a mine permit is initiated, often governments will impose a performance bond, money that has to be set aside and not used for the production of the mineral resource, but that money is left aside so it can be used for the purpose of reclaiming the land after mining has finished, even if the company goes out of business. So we do have methods for trying to go some ways towards ensuring that there's compliance with federal guidelines on reclamation, but they're not foolproof. And there's another point that I should make, is that when they talk about reclamation or restoring vegetation in an area to its original state, they have not restored the ecosystem. Typically, they leave behind very young vegetation, and they might have disturbed and removed a fairly mature ecosystem. So they're leaving behind a young ecosystem that still has yet to evolve. So it's not back to where it was when the mining process started, but typically our goal is to get the land back to a place where it can remain stable and evolve towards an ecosystem closer to what existed at the surface prior to mining. Underground mining is less common than surface mining for coal in the United States, but it too is going to have environmental impact, including acid mine drainage, subsidence, the issue of the surface caving in to when sediments in the roof of a mine fall in, and there's a cave-in causing disturbance of the ground above an underground opening. There's also the potential for coal fires. There are some coal seams that have been burning, smoldering for decades in parts of the United States, Pennsylvania, for example, and those fires in and of themselves can represent a significant environmental hazard. Acid mine drainage and disturbed watershed is one of the most obvious disturbances to an area in which coal mining has been occurring. There's also the basic removal of the land when you take off the overburden. Some people refer to some forms of this mining as mountaintop removal, but that is one environmental impact, but probably the most pervasive is the disturbance in the watersheds and the potential for acid mine drainage. Given these environmental impacts of coal mining, what are some of the implications for future use? In the United States in particular, we're going to have motivation to rely on our fairly abundant coal resources when there are oil and gas shortages. So when there are shortages in the available oil and gas supplies, or when the prices of those commodities go up, then we're probably going to be more naturally looking towards our coal resources. This will mean more strip mining, more surface mining operations to extract the coal. Another issue with coal mining is that after we burn coal, it leaves about 5 to 20% ash. It's a solid waste at that point that needs to be contained, and so we have a containment of the coal ash issue after we've taken advantage of the resource. It's also true, and this will be something that we talk about more when we get to our module on climate change and global warming, but coal has a very high carbon footprint. That in order to get a certain amount of energy out of coal, we have to burn an unusually high amount of it, and that produces a very large quantity of carbon dioxide, which we'll see plays a role in contributing to global warming. Careful planning and on how to mine the coal, how to extract the energy from coal can help to reduce the problems or minimize them, but it can't eliminate these inherent environmental challenges that are associated with the use of coal. Next, we'll look at oil and gas, which we can also clump together under the term hydrocarbons. When we look at crude oil and natural gas, which I can abbreviate as O&G, we're talking about hydrocarbons. And chemically, we're talking about various organic species that are made out of various quantities of carbon, hydrogen, and oxygen in different ratios. And these are formed from the transformation of organic matters. So again, we're burying organic matter deeply beneath sediments. And we'll talk about the process of how oil and gas form in a minute. But in order to take advantage of these mineral resources, we mine them through production wells. So they come up to us in the form of a liquid or a gas, typically, but there are other forms, and that is from oil shale, which we have significant reserves of in western Colorado and Utah and part of Wyoming, and also tar sands, which tend to be far more abundant in Canada than they are in the United States. In addition to oil, we also have natural gas. Now, natural gas is has a number of different gas chemical species that make it up, but the most important, or the largest portion of natural gas, is simply methane, CH4. How do we form oil and gas? It results from the rapid burial in an anaerobic or low oxygen environment. So we're taking carbon, plant and animal life, and we're burying it relatively quickly under sediments than in an environment that deprives it of available oxygen. Then through a biogenic, that is biologically based, or a thermogenic, that is temperature aided transformation, the organic matter progresses towards the formation of oil and gas. When the oil and gas is formed, it's often a gas which is very mobile, or a liquid which is more mobile, so it begins to move from the locations where it was generated in the subsurface and starts to migrate up towards Earth's surface. Oil and gas can become trapped over geologic time. And in fact, it needs to be trapped in order for us to be able to find it in Earth's surface. If the oil and gas that's produced isn't trapped, then it will eventually migrate towards the surface and dissipate at the surface without us ever noticing it. When we drill through sediments, we have what we can call an oil window that's approximately 3 to 6 kilometers in depth, at which the oil and gas is being formed. Sediments deeper than that are very unlikely to have any oil and gas present. They're typically too hot, that their temperatures get too high for oil and gas to remain stable at depths larger than about 6 kilometers. Oil and gas. Oil and gas form essentially from the process of organic material becoming buried to sufficient depth in a low oxygen environment such that the hydrocarbons begin to form. Those hydrocarbons are liquid or gaseous, so they begin to migrate up from their origin. So if this is the depth where the organic material can begin to degrade to hydrocarbons, they become liquid or gaseous and begin to move up through what's shown here as one of the beds that's more permeable, allows the passage of the oil and gas, and that would be something like sandstone or a fractured rock. But that material can't migrate up through an impermeable layer such as the gray one shown here, a shale. So instead of moving up vertically, it just moves up through the sandstone bed, the porous medium, and it continues to migrate up further until it gets to it's either going to reach the surface or become trapped by a particular type of geologic structures. If there was only sandstone above it, then all that material would just migrate to the surface and dissipate into the atmosphere and would never have known of its existence. That's happening all around us. In most environments where the hydrocarbons could form. They're not typically trapped. They simply migrate to the Earth's surface and dissipate into the atmosphere. But in certain geologic structures, we can actually trap the oil and gas. And, well, we don't trap. The oil and gases are trapped by this natural formation change. And we'll take a look at different types of materials that can be effective traps for oil and gas. When we look at the geology of oil and gas, we need to recognize that there are different kinds of rocks that are going to perform different functions. So we'll look at the geologic conditions that must be necessary for an oil and gas field. First, we're going to have some sort of source rock. This is a fine-grained, organic-rich sedimentary rock in which the once living material is resident and it subsequently becomes buried to a significant depth. Then that oil and gas migrates upward into the reservoir rock. So it leaves the source rock and enters the reservoir rock. The reservoir rock, in the last slide, you'll see that it was the sandstone. That is some sort of porous or permeable rock that allowed the oil and gas to migrate up to a shallower depth. And then it might go all the way to the surface, but in an effective oil and gas field, we'll need to have some sort of cap rock. And this is some impermeable rock that functions as a barrier to trap the oil and gas in place inside the reservoir rock, and thus that forms an oil field or a gas field. We'll take a look at these types of cap rocks and types of oil and gas traps in the next slide. There are three basic common oil traps that we're going to consider. The first is an anticline or anticlinal trap. The next is a fault trap. And lastly, we'll have an unconformity trap. And these are shown graphically in the following slides. So here's an anticlinal trap or an anticline trap. Here you'll see that we have a folded set of sedimentary beds, and the source rock was a shale, but the organic material left that shale, migrated up into the reservoir rock, the sandstone, and it continued to migrate vertically until it got to the low permeable shale that functioned as a cap rock and trapped the oil. So this is a classic anticlinal trap depicted here. Next, we'll look at a fault trap. There are lots of different types of structures for a fault trap, but again, what we have is a source rock, a reservoir rock, and a cap rock that works to create a trap for the oil and gas that was migrating upward vertically, and it became trapped at the upper edge of the cap rock, and you'll see that the fault shown as the black line here. The fault helps out in trapping the oil in place. Finally, we have the unconformity trap. In the unconformity trap, we have some unconformity shown here as this horizontal interface between the tilted beds and the horizontally deposited beds. And the source rock is again a shale that contained the organic material. That material degraded, became mobile, moved upward into the reservoir rock. It couldn't move up any more than it couldn't get into the cap rock, so instead it migrated up to be trapped here beneath this unconformity. So there's an unconformity trap. When we look at oil and gas production, our general process is we need to do some sort of exploration procedures to discover the presence of potential oil fields, and then once discovered, we need to commence with production. So we drill wells down to the depth where we believe the oil field is. Hopefully we find it, or else it becomes a hole that doesn't have any pay associated with it, and it's not economically viable. But when there is an oil or gas field discovered, then we can begin with production. During the first few years of production, we experience what's known as, we're in the phase of primary recovery. And typically there we pump about the first 25% of the petroleum in the field under the natural reservoir pressure. So we're just withdrawing the easy portion, the first 25% that comes out under the pressure of the reservoir field. Then we have to use enhanced technique to try and continue with production, and so it's called enhanced recovery. Here we manipulate the reservoir, typically by injecting gases or liquids, and we can use that to get about 50 or 60% of the petroleum that's in that field. But we're still leaving behind about 40 to 50% of the oil and gas that were in the formation to begin with. So in primary recovery, we get the first 25, then we can get another 25 or 35% through enhanced recovery methods, but we leave some of the oil in place. We have tertiary recovery that are sort of the cutting edge or research component of production, but we're continuing to look for efficiencies to try and get more oil and gas out of each oil and gas field that we discover. When we look at the global distribution of oil and gas, there's a few things that we can observe. First, we're producing almost exclusively from sedimentary rocks that are younger than 500 million years old. Any old units older than that, and they simply don't have productive oil fields. Also, most of the total production of oil and gas is occurring in just a few percent of the world's producing fields. So just a small fraction of the total oil and gas fields around the globe produce the largest quantity of oil and gas we're currently extracting. Also, most giant oil and gas fields are near relatively recently active plate boundaries. So again, we've got a tie here between resource distribution and plate tectonics. In the middle of a long, stable plate, we don't find large oil and gas fields. They tend to concentrate near recently active plate boundaries. We showed a distribution of coal in the last module across the globe. Now we're going to take a look at oil reserves and their distribution around the globe. The poor Middle East that didn't have much oil and gas, we see, have quite a bit of oil reserves, as they're well known for that quantity, while North America had an abundant amount of coal. A more modest fraction of the world's oil reserves are present in North America. South America, that seemed to be a bit shortchanged in the coal distribution, has a larger portion of oil reserves available to it. Africa all had a modest quantity of coal, but has a larger fraction of the world's oil fields. Eurasia has a significant fraction of the world's oil reserves, and Southeast Asia and Australia have a relatively modest fraction of the world's oil fields. Next, we'll turn our attention to natural gas. We have a larger global reserve of natural gas than we do of oil. We expect that our natural gas reserves should last another 100 years at the current rate of consumption. We have a relatively high percentage of those reserves in Russia and the Middle East. Natural gas tends to be a cleaner fuel than oil or coal. It has a higher energy content and it has a lower carbon footprint, a fact that'll come up when we talk about climate change. Lastly, there are some unusual locations where we can extract natural gas, such as coal bed methane. All coal beds contain some degree of methane, and if we extract the methane prior to producing the coal, we can actually make the first phase be the extraction of the natural gases, and the second phase be extraction of the coal. In addition, we have tight natural gas from shale that is well known to us as coming to us in the form of what we know as fracking, which is effective in some locations and in other locations is a suspect in contamination of groundwater resources. Another novel potential source for natural gas are methane hydrates that you can read about in your textbook. These provide potential alternative energy sources compared to our current conventional resources. Next, we'll turn our attention to the impact of petroleum production. After the exploration and initial drilling phases, we enter the producing stage of an oil and gas field, and we increase the amount of land disturbance at the producing field in this stage. We need to get access for drill rigs, for drilling the producing well and associated injection wells in the vicinity, for getting the transportation, for transporting the produced fluids from the producing site to the refinery. We're going to have increased land disturbance. So at the surface we have a lot of disturbance, but we'll also have continued impacts in every stage. So we'll have environmental impacts at the production site, along transportation lines, whether that's by pipeline or rail line or in trucks on the roadway. We'll also have potential environmental impacts, and then we'll have emissions finally in the last stage of the oil and gas production at the refinery, where we're creating whatever products we're getting, such as gasoline at a refinery from the crude that we produce from the ground. We also have a number of byproducts that are typically left at the production location, where at the surface above the producing field. When we extract oil or gas, we typically extract salty brine water with it. And we usually let them separate at the producing location, and we'll often store the brine water briefly and then pump it back down into the formation from which we extracted it, but not before some of it evaporates typically. If there's enough evaporation, that brine water will leave behind salty deposits that we have to treat as a waste product and dispose of it at some other locations. So typically that's an additional cost, an additional stage of keeping a production site clean. Occasionally, the salts that are left behind have naturally occurring radioactivity within them that cause us to have to use increased precautions when disposing of those wastes. And that's not that rare. Those happen on a regular basis. You might not have been aware that every time you pump gas into your car, you're generating a bit of nuclear waste at the production site where the gasoline was originally, the crude oil was originally extracted from the subsurface. When we have an oil field that's been developed in a sensitive area, that means our potential for environmental impacts are much greater. And we'll take a look at some locations where that's under active debate of how to reduce the environmental impacts in particularly sensitive areas. The reality is that we have, on a regular basis, blowouts, fires, oil and gas oil spills, and it might be at the actual production location. It might be at some point along the transportation line, along a pipeline, for example, in a tanker ship carrying crude to a refinery, or even along a roadway when some of the products are spilled at the surface. So we have oil spills that are possible everywhere. Some people regard them as inevitable because mistakes do happen. Lastly, in the production of oil and gas, we have the formation of acid rain, and I'll talk a bit more about this in a few moments. The Arctic National Wildlife Refuge in northern Alaska is one location where we may have some suspected oil reserves that we're currently not producing. Right adjacent to the Arctic National Wildlife Refuge, we have the Trans-Alaska Pipeline, where crude oil is being piped north to Prudhoe Bay, and that's a location where we have a pipeline in place. A lot of people and a lot of oil and gas companies have lobbied for the right to explore and produce oil and gas from the Arctic National Wildlife Refuge, but currently that's not being allowed. But it comes up for debate on a regular basis. As a nation, we get to decide what the value of the natural resource of having a wildlife refuge is compared to the potential value of producing oil field for the decades during which it might be able to produce resources that we currently find valuable. So we're all going to have the opportunity to continue to contribute to this debate about whether to leave the wildlife refuge or to begin producing what may be, they're not yet discovered oil fields in that area, but there are adjacent fields, so it's suspected that there might very well be oil and gas fields under this area as well. It is true that we have new technologies in oil drilling and transportation that can help reduce the impact on the environment from production. This image is trying to depict the fact that we used to think of drilling as being an entirely vertical process. That is, you sink a boring to whatever depth of interest, but new technologies allow us to use directional drilling that use one site to drill off in many directions and would have the potential to extract from different fields that are in a region. I think this image depicts an unusually rich set of oil fields that you might be able to produce from using a single site at the surface. But directional drilling certainly allows us to use new technology to reduce environmental impact. We'll need fewer roads. We'll need fewer production sites. So that'll reduce our total land disturbance. Another thing that's being depicted here is that it's proved to be possible to have pipelines moving the crude oil toward the refinery that have a reduced impact on wildlife. Here's a depiction of what's meant to represent or meant to document that wildlife aren't necessarily disturbed by production pipelines, but we hear on a regular basis about spills along these pipelines, but certainly we can take efforts to reduce those. I just don't mean to try and sell this as a impact-free method of transporting crude oil. When we think about the future of oil, we can recognize that recent estimates tell us that oil and natural gas will last at least a few more decades. When will we experience our oil production peak? We don't know at this time. Once production does peak, we'll find that after that peak, we'll have less oil available to us for use, and we'll start to experience price shocks, which will have significant economic impact. More on the future of oil. We have evidence of an impending crude oil crisis. The time is approaching when 50% of total oil crude from traditional fields will have been consumed. Our world consumption currently is at 31 billion barrels per year, and at the present time, for every 3 barrels that are being used or extracted, we're currently discovering about 1. So the rate at which we're discovering additional potential fields is currently not keeping up with the rate at which we're extracting oil. Thus, we expect the peak of world crude oil production to be sometime between 2020 and 2050. We also expect that we're not going to have significant production in the United States beyond 2090. What can we do in response to these projections of this future of reduced amount of oil being available to us? Well, through education, we may be able to use less oil and gas. We can take advantage of new energy resources, seek the development of new energy resources before we reach peak production, and thus try and avoid some of the worst of the price shocks that could be anticipated after peak oil production. Next, I want to take up acid rain. Fossil fuel burning naturally leads to the production of acidic precipitation or acidic acid rain, although sometimes we have acid snowfall, but it's most commonly an acid rain. It tends to be a regional or a global problem. It's not typically confined to a single state, for example. It's generated by a reaction of sulfur and nitrous oxides with water. It can lead to acidic rainfall that has a pH lower than 5.6. That acidic rainfall will have effects that depend on the bedrock, the soil, the water characteristics of the location where the acid rain is falling, and it can cause significant damage to vegetation, to lake ecosystems and to human structures. How does acid rain work? We typically find that pollutants that come from fossil fuel burning, such as sulfur dioxide, nitrous oxides, are pumped into the atmosphere. Those pollutants are transported by winds in the upper atmosphere to locations somewhere downwind. They combine with precipitation to create slightly acidic precipitation. It is not at all uncommon to think of this as a conveyor of production of high pollutant containing coals in the Dakotas, for example, generating pollution that blows downwind towards eastern Canada and northeastern United States and creates a significant acid rain problem. Many states downwind from the refineries or energy power plants that were taking advantage of the fossil fuels. So one of the inherent problems with acid rain is that the governments that could regulate the burning of fossil fuels may not have the motivation to, because the states that are affected by the acid rain might be some significant distance downwind. To help understand what a pH of less than 6 would be, we can look at the pH scale. And if we have a neutral pH reading, it'll be a pH of about 7. If we look at something that's very acidic, like lemon juice or vinegar, we get down to pH measurements in the range of 2 to 3. In the 1930s, the mean pH of Adirondack lakes in upstate New York was around 6.6, but the pH had fallen below 5 by 1975 due to acid rain. If we have a relatively pure rain in the northeast United States, it could typically have a pH of around 5.6 now because of the effects of acid rain. The first snowfall of the year is often found to be one of the most acidic precipitations that falls to Earth. So there's a bit about the pH scale. Another thing that has to be present for acid rain to be a problem is that you need to have an ecosystem where the vegetation or lakes have a natural sensitivity to the pH of the rain falling on Earth's surface and infiltrating into the ground. We have some locations that have a relatively low sensitivity to acid rain and some areas that have a relatively high sensitivity. It just so happens that in the northeast United States and eastern Canada, we have some high sensitivity ecosystems that are currently experiencing some significant acid rains from burning of fossil fuels someplace upwind. I had mentioned that acid rain can also have impact on human structures, and here's some marble antiquities that show the weathering effects from acid rain. Acid rain will actually help to dissolve marble, so that leaves building stones and monuments susceptible to erosion from acid rain. Lastly, we'll look at fossil fuels and acid rain and trying to identify some solutions. In local areas, in some cases, it's possible to use techniques such as adding calcium carbonate to a sensitive lake to try and buffer the pH and to reduce the effects of the low pH rainfall. We add something that has a relatively high pH to balance out the work of the acidic water by adding something that turns the lake to something more of a base or more neutral pH levels. But the only long-term practical solution to acid rain is to reduce the total emissions associated with fossil fuel burning. And we can do that through conservation and burn less fuel, or we can improve the scrubber techniques in coal burning, for example. So we can treat the byproducts of coal burning to try and reduce the total potential for acidic rain. But burning less fossil fuel is the only long-term complete solution to the acid rain problem.